Hello everyone. Today we will discuss equation of motion under central force and first integrals. Here let us consider a particle of mass m is moving about a fixed center O, and let us say its radial distance from the point O is r. Then you know that we can define the central force in vector form as F is equal to Fr unit vector r. You know unit vector r is equal to vector r upon modulus r. So it will be equal to Fr vector r upon vector r modulus. Because F is a central force, so we can write Fr as equal to minus del V over del R. Here V is potential energy as it is function of the distance only. So force here will be equal to minus del V over del R into vector R divided by modulus of the vector R. Let us say it is equation number 1. You know that here the motion is taking place in a plane, so we can write here plane polar coordinates, and Lagrangian for such a system will be equal to kinetic energy minus potential energy. Kinetic energy in plane polar coordinates we can write as 1 by 2 m r dot square plus r square theta dot square minus Vr, it is potential energy. Let us say equation number 2. Here in equation number 2 you can see that theta is not present, so we will consider here it as a cyclic coordinate. So we can write del L over del theta is equal to 0. Now if we write the value of del L over del theta is equal to 0 in Lagrangian condition, then you can see that del L over del theta dot will be equal to constant, and we know that del L over del theta dot is equal to p theta, which is called as the angular momentum or generalized momentum in terms of the angle. So p theta is equal to mr square theta dot, and it is a constant, so we can represent it by j also. Let us say it is equation number 3. Now as j is equal to mr square theta dot and it is constant, the mass of the particle is not going to be changed, so we can write it as r square theta dot is equal to constant, or we can write here 1 by 2 r square theta dot is equal to constant. When we multiply 1 by 2 to r square theta dot, it will not affect because it is equal to a constant quantity. So we can write here r square theta dot equal to a constant is equal to 1 by 2 r square theta dot, and it is also equal to a constant. Let us say it is equation number 4. Now this quantity 1 by 2 r square theta dot, we can write it as, if we see the area swept out by the mass m in a small time dt, then it will be equal to 1 by 2 r into r d theta. Here you can see that this is the distance r, and when p dash is very close to p, then we can write this as, because angle is equal to arc upon distance, so we can write it as equal to r. So arc will be equal to r into d theta. So it becomes a triangle. We can find the area as 1 by 2 base into height, and it is r d theta. So it becomes to 1 by 2 r square d theta. Now we can find the areal velocity, so we will divide it by time, and it will be equal to 1 by 2 r square d theta upon dt. So it will be equal to 1 by 2 r square d theta upon dt. Then we will say that areal velocity of the body will remain constant. This is the second law of the Kepler's for the planetary motion. Now we can write Lagrangian in terms of the r coordinate. it will be equal to d over dt del L over del R dot minus del L over del R equal to 0. Let us say it is equation number 6. And we know that Lagrangian is equal to 1 by 2 mr dot square plus r square theta dot square minus Vr. So here we can find the value of del L over del R dot and del L over del R. If you see here, del L over del R dot will be equal to mr dot and del L over del R, it will be equal to mr theta dot square minus del V over del R, because V is a function of R. Let us say these are equation number 7. Now we will put these values in equation number 6, which is the Lagrangian condition for R coordinate. So we will write d over dt mr dot minus mr theta dot square plus del V over del R is equal to 0. It will be equal to mr double dot minus mr theta dot square, and del V over del R, it will be equal to minus fr. So we will write it as minus fr is equal to 0. Or we can write mr double dot minus mr theta dot square is equal to fr. Let us say it is equation number 8. We also know that j is equal to mr square theta dot. So theta dot will be here j upon mr square. Now we can write here equation number 8 in terms of the angular momentum. So it will be equal to mr double dot is equal to j square upon mr cube minus del V over del R. Or we can write it as minus 1 by 2 del over del R j square upon mr square minus del V over del R. Let us say it is equation number 9. Now we can also arrange the earlier equation as mr double dot is equal to minus del over del R in bracket 1 by 2 j square upon mr square plus V. Now let us solve this equation. For solving this equation, we multiply both sides by r dot. Then it becomes mr double dot into r dot is equal to minus del over del R in bracket 1 by 2 j square upon mr square plus V into r dot. Let us say it is equation number 10. Now we can write it as differentiation of 1 by 2 mr dot square, and it is differentiation of minus j square upon twice mr square plus V. Or we can write it as d over dt 1 by 2 mr dot square plus j square upon twice mr square plus Vr equal to 0. Now if we integrate this equation, then we can write it as 1 by 2 mr dot square plus j square upon twice mr square plus Vr is equal to constant, and it is equal to capital E, which is the total energy of the system. Let us say it is equation number 11. If we put here j is equal to mr square theta dot, then above equation can also be written as 1 by 2 m r dot square plus 1 by 2 mr square theta dot square plus Vr is equal to E, and it is also equal to constant. The equation 11 and 12 are called as the first integral equation of motion, and these results are very important and will be used in central force problems. So you have to remember this expression 11 and 12. Thank you.